Welcome to today's session. In this video, we'll be tackling LeetCode problem number 1060, missing element in sorted array. This problem focuses on finding the kth missing number in a sorted array, which tests your understanding of array manipulation and efficient algorithms. Let's dive in and explore the approaches to solve this challenge. In this problem, we are working with a sorted integer array called nums and an integer k. The array is in strictly increasing order, meaning no duplicates and the values grow consistently. However, some integers are missing from the sequence. For example, if nums is 4, 7, 9, 10, the missing integers are 5, 6, 8. To solve the problem, we define a function called missing, x, which tells us how many integers are missing between the start of the array, nums, 0, and the element at position nums, x. The formula for this is missing, x equals nums, 0, x. Our task is to find the kth missing number, starting from nums, 0, and return it as the result. Let's look at some examples to understand the problem better. In the first example, the input nums is 4, 7, 9, 10, and k is 1. Here, the missing integers are 5, 6, 8. Since k is 1, we are tasked with finding the first missing number. By observing the sequence, we see that the first missing number is 5. Therefore, the output for this example is 5. In the second example, the input remains nums equals 4, 7, 9, 10, while k is now 3. The missing integers are still 5, 6, 8, but this time we need to identify the third missing number. From the sequence, the third missing number is 8. Hence, the output for this case is 8. In another example, let's consider nums equals 1, 2, 4, and k equals 3. The missing integers are 3, 5, 6. Our goal is to find the third missing number. By examining the sequence, the third missing number is 6, so the output is 6. The reason the output is 6 in the previous example is that the missing integers follow the natural sequence of numbers. The first missing number is 3, the second is 5, and the third is 6. Now let's review the constraints for this problem. The length of the nums array can range from 1 to 50,000. Each element in nums is a positive integer between 1 and 1 billion. The array is strictly increasing, meaning no duplicates, and the value of k is between 1 and 10,000. These constraints ensure that the input is well defined and that we can handle large arrays and values. When thinking about edge cases, consider scenarios like a small input size. For instance, if nums equals 1, 100, and k equals 50, the missing numbers are 2, 3, 51, so the output is 50. Another edge case involves large input values. If nums equals 10 to the power of 9, 2, 10 to the power of 9, 1, and k equals 2, the missing numbers are 10 to the power of 9, 1, 10 to the power of 9, and the output is 10 caret 9. Additionally, if k is larger than the gaps in the array, such as nums equals 1, 2, 4, and k equals 5, the missing numbers extend beyond the array, and the output is 8. Lastly, if there are no missing numbers within the range of nums, like in nums equals 1, 2, 3, 4, with k equals 1, we still look for the first missing number beyond the array, which in this case is 5. To begin, the brute force approach uses a straightforward but inefficient method to find the kth missing element. The intuition here is simple: iterate through all the numbers between the smallest and largest values in the array nums, and keep track of how many numbers are missing. For each number in this range, we check whether it exists in nums. If it doesn't, we count it as missing. Once the count of missing numbers reaches k, we stop. However, this approach has significant drawbacks. The primary issue is its inefficiency. Checking whether each number is missing requires repeatedly searching the array, which can make this method extremely slow for large inputs. With a time complexity of n squared, it is computationally expensive, though it does have the advantage of requiring no additional space beyond the input array. Still, the inefficiency makes it impractical for most real-world scenarios. Now, to address the inefficiency of the brute force approach, we turn to an optimized solution using binary search. The key idea is to avoid iterating through every number in the range and instead locate the kth missing number more efficiently by leveraging the sorted nature of the array. We calculate the total number of missing numbers at each index I using the formula nums, 0, I. This formula tells us exactly how many numbers are missing from the sequence up to nums, I. Importantly, the number of missing numbers increases strictly as the index increases, which allows us to use binary search to pinpoint the smallest index I where the kth missing number could be located. We start by initializing low and high to the bounds of the array. Through binary search, we narrow down the range until we identify the correct index. Once the search converges, we calculate the exact missing number using the relationship between the missing count and the values in the array. This approach is both efficient and elegant, as it reduces the search space logarithmically. The binary search approach offers significant advantages in terms of complexity. With a time complexity of O log n, it is much faster than the brute force method, particularly for large arrays. Additionally, it has a space complexity of O(1), meaning it does not require any extra memory beyond the input data. This efficiency comes with a trade-off. While the brute force method is easier to understand, the binary search approach requires a deeper understanding of the missing count formula and careful implementation. Despite this, the binary search approach is the clear choice for solving the problem efficiently. By leveraging the strictly increasing property of the missing count, we can locate the kth missing number in a highly optimized manner. This strategy balances runtime efficiency with implementation complexity, making it the most robust and scalable solution for this problem. The ability to reduce the problem to a logarithmic search while maintaining constant space usage highlights the power of this approach. To solve the problem of finding the kth missing positive number in a sorted array, we start with a simple brute force approach. First, we need to initialize two counters. The first counter, missing_count, will track the number of missing positive integers we have encountered so far. The second counter, current, is used to iterate through all integers starting from 1. Initially, missing_count is set to 0, as we haven't encountered any missing numbers yet, and current is set to 1 so we can begin checking from the smallest positive integer. The next step involves iterating until we find the kth missing positive number. We use a while loop that runs as long as missing_count is less than k. For each value of current, we check whether it exists in the nums array. If the value of current is not in nums, it means that this number is missing. In that case, we increment missing_count by 1 and check if it matches k. If it does, we return current as the kth missing number. If current is found in nums, we simply skip it without incrementing missing_count. Regardless of whether the number is missing or not, current is incremented by 1 at the end of each iteration, so we can evaluate the next integer. This brute force approach has some important insights that make it straightforward to understand. First, it uses a linear search to identify missing numbers one by one, starting from 1. While this method is simple to implement, it can become less efficient for larger inputs. Second, the algorithm relies on the AND operator to check whether a number exists in the sorted array nums. This operation, while convenient, has a time complexity of O(n) for each membership check. Finally, the algorithm stops immediately after finding the kth missing number, which helps avoid unnecessary iterations and ensures that the process terminates as soon as the result is determined. The algorithm uses only a few data structures to operate. The primary data structure is the input array nums, which is sorted and used to check if a number exists. All membership checks, such as current in nums, are performed on this array repeatedly. Additionally, there are two counters, missing_count and current. The missing_count counter helps us keep track of how many missing numbers we've encountered so far, while current allows us to iterate through integers sequentially, starting from 1. Together, these simple data structures enable the algorithm to function without requiring complex setups. There are several edge cases to consider when applying this algorithm. In cases where all missing numbers are smaller than the smallest number in nums, such as when nums is 10, 20, and k is 5, the algorithm simply iterates from 1 to 5 and identifies them all as missing. Another edge case occurs when k exceeds the range of numbers in nums. For example, if nums is 1, 2, 3, and k is 5, the algorithm continues iterating past the largest number in nums to find the kth missing number. Finally, there's the scenario where there are no missing numbers before k. For instance, if nums is 1, 2, 3, 4, and k is 1, the algorithm correctly identifies the next number outside the range of nums, which is 5, as the first missing number. Let's analyze the complexity of this brute force approach. For time complexity, the outer while loop runs until the kth missing number is found. For each iteration, the algorithm performs a membership check, current in nums, which has a complexity of O(n). In the worst case, the loop can run up to O(k) times, resulting in an overall time complexity of O(n*k). As for space complexity, the algorithm does not use any additional data structures beyond the input array and 2 counters. Therefore, the space complexity is O(1), making this approach memory efficient despite its higher time complexity for larger inputs. This implementation solves the LeetCode problem number 1060, missing element in sorted array, using a binary search approach to efficiently find the kth missing positive number. Explanation. 1. Helper function. A helper function missing_count, IDX, calculates how many numbers are missing up to a given index IDX. The formula nums, IDX, nums, 0, IDX computes this by comparing the actual range of numbers with the expected range for a continuous sequence. 2. Edge case. If k exceeds the total number of missing numbers in the array, i.e., k missing_count, n1, the kth missing value will be beyond the last element. In this case, we calculate it directly as nums-1 plus k missing_count, n1. 3. Binary search. The core optimization is a binary search to locate the interval where the kth missing number falls. The algorithm maintains 2 pointers, left and right, and iteratively narrows the search range. At each step, the midpoint mid is calculated. If the missing count up to mid is less than k, it means the kth missing number lies to the right, so left equals mid plus 1. Otherwise, it lies to the left, so right equals mid. 4. Final calculation. After the binary search, left points to the smallest index where the missing count is greater than or equal to k. The kth missing number is then calculated as nums, left 1, plus k missing_count, left 1, as it lies between nums, left 1, and nums, left. Complexity. Time complexity, the binary search runs in O log n, and the missing calculation is O(1), resulting in an overall complexity of O log n. Space complexity, the algorithm uses O(1) additional space. This solution is efficient and handles edge cases like k being larger than the total missing numbers or arrays of minimal size, making it suitable for competitive programming and real-world applications. Here, we start by defining a helper function called missingCount, which calculates the number of missing elements up to a given index IDX. This is done by taking the difference between the value at nums, IDX, and nums, 0, and then subtracting the index itself. Next, we move to the main function missing element, which takes the sorted array nums and an integer k representing the position of the missing element we're trying to find. First, we calculate the total number of missing elements up to the last index of the array. If k is greater than this count, it means the kth missing number lies beyond the end of the array. In that case, we simply return the last element of the array, nums, n1, plus the difference between k and the missing count at the last index. This handles the edge case where the missing number falls outside the current range of the array. If the kth missing element lies within the array, we use binary search to locate it efficiently. The goal is to find the smallest index where the missing count is greater than or equal to k. We initialize 2 pointers, left and right, to represent the search range. While left is less than right, we calculate the midpoint, mid, and check the missing count at mid. If the missing count is less than k, it means the kth missing number lies further to the right, so we adjust left to mid plus 1. Otherwise, we narrow the search range by setting right to mid. Once the binary search concludes, the kth missing number is determined to lie between nums, left 1, and nums, left. We return the value by adding the difference between k and the missing count at left 1 to nums, left 1. Finally, the function completes with this return statement, efficiently solving the problem using the combination of arithmetic and binary search. To solve this problem, we start by understanding the input and the goal. We are given a sorted array, nums equals 4, 7, 9, 10, which skips certain numbers in the sequence. The task is to find the first missing number, with k equals 1. Next, we introduce a helper function called missing_count, IDX. This function calculates how many numbers are missing from the start of the array up to a specific index. The formula is missing underscore count, IDX, equals nums, IDX, nums, 0, IDX. For example, at index 3, the total count of missing numbers is calculated as 10 4 3 equals 3. Now, we check if the kth missing number is beyond the array. Since the total missing count at the last index is 3, and k equals 1 is less than that, we know the first missing element is within the array itself. The next step is to use binary search to locate the smallest index where the missing count is at least k. Initially, left is set to 0 and right to 3. In the first iteration, we calculate mid equals 1 and find missing underscore count, 1 equals 7 4 1 equals 2. Since this is greater than or equal to k, we update right equals mid, making right equals 1. In the second iteration, we recalculate mid equals 0 and evaluate missing underscore count, 0 equals 4 4 0 equals 0. Now, since missing underscore count, 0, is less than k, we update left equals mid plus 1, making left equals 1. At this point, left represents the index where the kth missing number lies. Specifically, it's between nums, left 1 equals 4 and nums, left equals 7. Using the formula result equals nums, left 1, plus k missing underscore count, left 1, we calculate result equals 4 plus 1 0 equals 5. Therefore, the first missing number is 5. Now, let's explore two additional examples to solidify our understanding. For nums equals 1, 2, 4, and k equals 3, we first calculate the total missing numbers in the array as missing underscore count, 2 equals 4, 1 to 2 equals 1. Since k equals 3 is greater than this, the third missing number is beyond the array. We compute result equals nums, dash 1, plus k missing underscore count, n1, which gives result equals 4 plus 3, 1 equals 6. Thus, the answer is 6. In the second example, nums equals 3, 6, 8, 10, and k equals 4. Here, the total missing count is missing underscore count, 3 equals 10, 3, 3 equals 4. Since k equals 4 matches this count, the fourth missing number is just beyond the array. Using the same computation method, we find result equals nums, dash 1, plus k missing underscore count, n1, which gives result equals 10 plus 4, 4 equals 10. Hence, the answer is 10. The time complexity of this function is primarily influenced by two components, the helper function missing underscore count and the binary search. First, the missing underscore count function calculates the number of missing elements up to a given index IDX. Since it involves a simple mathematical expression with one subtraction and one addition, it runs in constant time, or O1. Now, the binary search is the main contributor to the algorithm's time complexity. By systematically having the range of possible indices, binary search narrows down the location of the kth missing number. Starting with a range of size n, the search requires approximately log 2, n, iterations. In each iteration, the missing underscore count function is called once to determine whether the current midpoint satisfies the condition. This makes the binary search process run in O log n time. Together, the binary search and the O1 helper function calls result in an overall time complexity dominated by O log n. To handle edge cases, such as when the kth missing element lies beyond the array, the algorithm performs a simple check using missing underscore count. Specifically, the condition if k missing underscore count n1 involves two calls to missing underscore count, each taking O1 time. These operations are negligible compared to the logarithmic cost of binary search. Thus, the overall time complexity remains O log n, as the binary search dominates the runtime. Now, considering space complexity, the function requires very little additional memory. The input array nums is external to the algorithm and does not count toward auxiliary space usage. The helper function missing underscore count operates directly on the input data without creating new data structures, and the binary search uses a small number of integer variables, such as left, right, and mid, which occupy constant space. Therefore, the algorithm's space complexity is O1, making it highly efficient in terms of memory usage. In summary, the overall space complexity of this function is O1, since it does not allocate any additional data structures or use extra memory beyond a few variables. To understand the efficiency of this approach, let's compare it to a brute force solution. A naive method would iterate through the entire range of integers from nums 0 to nums -1, or even beyond, counting missing numbers one by one. This would require a loop that iterates through all numbers, leading to a time complexity of O(m), where m is the difference between the largest and smallest numbers in the range. Despite using O(1) space, this brute force approach is far less efficient. In contrast, the optimized solution leverages the sorted nature of the array in binary search to achieve O log n time complexity, which is significantly faster, particularly when the array is sparse and n is much smaller than m. This optimized approach also maintains O(1) space complexity, providing the best balance of speed and memory efficiency. Analyzing the algorithm further, we see that its performance varies slightly depending on the scenario. In the best case, where the kth missing element lies beyond the array and the condition k missing underscore count n1 is satisfied, the algorithm directly computes the result in O(1) time, requiring no binary search. On average, the binary search performs log n iterations, with each iteration taking O(1) time, resulting in an average time complexity of O log n. In the worst case, the algorithm completes the full binary search process, which still runs in O log n time. To mathematically confirm the time complexity, consider that the binary search halves the range of indices with each step. After log 2 n steps, the range reduces to one element, and since each step involves constant time operations, the total time complexity is O log n multiplied by O(1), which simplifies to O log n. The space complexity remains O(1), as no additional memory is allocated. This combination of logarithmic time and constant space makes the algorithm highly efficient compared to linear approaches. When solving this problem, there are a few common mistakes to be aware of. First, it's important to account for missing elements that fall outside the range of the array. For example, if k is larger than the total number of missing elements within the range of the array, you need to account for the numbers beyond the last element. A common error is to simply add k to the largest number in the array, which is incorrect unless you first verify the total missing count within the range and handle any excess appropriately. Another frequent issue is off-by-one errors when counting missing numbers between indices. The difference between two consecutive numbers in the array -1 gives the count of missing numbers, so the formula nums I1 1 ensures accurate results. Finally, avoid brute force approaches, especially for large arrays. Iterating through every number between the smallest and largest values can be inefficient, resulting in O n plus k time complexity. A better approach is to use binary search, which reduces complexity to O log n and is much faster. Another challenge is not considering edge cases, which can lead to unexpected errors. For instance, what happens if the input array contains only one element? Or if k is larger than the total number of missing numbers across and beyond the array? Negative numbers in the input can also add complexity. To address this, explicitly test for these edge cases and handle them early in your implementation. Additionally, it's crucial to fully understand the problem constraints. For example, the array is guaranteed to be sorted and contain unique elements, so you don't need to check for duplicates or sort the array yourself. Misunderstanding these constraints can lead to unnecessary checks or incorrect assumptions, which waste time and resources. Always carefully read and rely on the given constraints to streamline your solution. In interviews, focusing on efficiency and clarity is essential. Brute force solutions are rarely acceptable, so discussing the trade-offs between approaches like linear search and binary search demonstrates your understanding of algorithmic efficiency. This problem is a great opportunity to showcase specific patterns, such as working with sorted arrays, leveraging binary search to optimize counting or searching tasks, and systematically handling edge cases. Clear communication is another key factor. Explaining how you calculate missing numbers between ranges and how you handle special cases will give the interviewer confidence in your thought process. Also, remember to test your solution thoroughly. Use small arrays to validate your logic, large arrays to confirm efficiency, and edge cases to ensure robustness. This systematic approach will highlight your preparedness and attention to detail. This problem has several closely related variations that are worth exploring. For instance, LeetCode 1539, kth missing positive number, focuses on scenarios where the array starts at 1, which introduces slight differences in handling missing numbers compared to arbitrary starting points. The problem at hand, LeetCode 1060, emphasizes the use of binary search for efficiency, making it a great practice problem for honing this skill. LeetCode 268, missing number, is a simpler version where exactly one number is missing in a sequence, which can often be solved with mathematical formulas or XOR operations. Lastly, LeetCode 448, find all numbers disappeared in an array, shifts the focus to finding all missing numbers in O(n) time, introducing new constraints and optimization challenges. Exploring these related problems will deepen your understanding of common patterns and techniques. There are several approaches to solving this problem, each with its own trade-offs. A brute force method, or linear search, involves iterating through the array to find missing numbers. While simple, it has a time complexity of O(n plus k, which can become inefficient for large arrays or large values of k. Binary search is a more efficient alternative with a time complexity of O log n. However, it requires careful implementation, especially to handle edge cases. Another option is mathematical calculation, which can be used for arrays starting at 1 and following a continuous pattern. This approach directly computes the kth missing number but is limited to specific constraints. Lastly, for unsorted arrays, converting the array to a hash set allows for efficient lookup while iterating through numbers, with a time complexity of O(n) for setup and O(k) for searching. This approach uses extra space but is effective when sorting isn't guaranteed. Choosing the right method depends on the problem's constraints and the trade-offs you're willing to make. Great job! To wrap up, we reviewed efficient ways to find the kth missing element in a sorted array, discussed key insights, and highlighted the importance of optimization. Thanks for joining, and we encourage you to practice similar problems to solidify your understanding. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!